Let us look at the resistor capacitor circuit and how differential equation would apply to it. Alright? Now, we have a voltage source here. Let's call this V. We have our resistor here and our capacitor here. The voltage source is varying, right? Could be alternating current. What we want is a varying voltage source. Now, V, let's call this VT, applied voltage. We could consider T as total voltage, is equal to VR, voltage across the resistor, plus VC, the voltage across the capacitor. Now, the voltage across the resistor is IR, alright? But the current, if we consider it, the resistance, or rather the current flow, depends on, it is really the rate, not depends on, it is really the rate at which the capacitor is charging or discharging. If the capacitor is not being charged nor discharging, the current is zero. The faster the capacitor is charging or discharging, the higher the current. Because you're talking about a changing charge versus time. Alright? So, you can say I is dq by dt, the rate at which the capacitor is charging or discharging. So therefore, substituting I here, this I there, we say voltage across the resistor is R, let's put R on the left and I on the right, R times dq by dt. Alright. Now let's look at the capacitance itself. Right? We know that for the capacitor, the amount of charge depends on the capacitance and the voltage. So Q is equal to CV. Right? So that the voltage VC, alright, see in the wrong place, VC is going to be equal to the charge divided by the capacitance. Now, let's put these together. V, the applied voltage, is equal to R dq by dt plus Q over C. Alright? Now let us put V on the other side. That is equal to V. Now, this looks somewhat like a differential equation. First order differential equation. Remember the differential equation that is in the form dy by dx plus py equal q it looks somewhat like it. So let's do our necessary work on it and write it in that form. Now, here, we're going to have to divide both sides by r. So we have dq by dt. Maybe write the dt by dt plus, remember we're dividing by r, so that we have dq by dt. This will be q divided by rc, which you can write as 1 over rc times q equal v divided by r. Alright. Now in this case, the p is in the same position as the 1 over rc, right? And you remember, when you solve this, you multiply by the integrating factor, which is e to the integral of p dx. Remember that. We're going to do the same thing here. In this case, the integrating factor is equal to e to the integral of 1 over rc. Now remember, we're differentiating with respect to time, not x, is dt. So this is dt. Now what does this turn out to be? This is e to the, well, now consider r and c are constant, so 1 over rc is a constant, and you're integrating with respect to t, so you get t times a constant. So what you get is t divided by rc. Alright, good. You see that? Now the next step is to multiply both sides of the equation by e to the why am I scrolling all the way up there? This is the equation, right? Multiply both sides by this, of this, by e to the t over rc. So let's do that. So we have e to the t over rc dq by dt plus e to the t over rc times 1 over rc times q equal e to the t over rc times v over r. So there you go with that. Now, you are looking for what happens here. You know that it should be the result of differentiating a product. But what was that product? Let us see. Here, you differentiate q with respect to t. Right? Right there. This is the derivative of q with respect to t. And right here, you hold q as it is. By the way, remember, that when you differentiate using the product rule, you have two functions, u multiplied by v. So the derivative of uv with respect to x, if you use x, would be you hold u as it is times differentiate v with respect to x, find dv by dx, plus you hold v as it is times differentiate u with respect to x. Now in this case we're using t, so all these x's we could write them as t. So we're differentiating all of these with respect to t. Alright? Now the thing is, here, alright, let me just box this around because it's not part of the working. Here now, obviously, you found the derivative of q with respect to t. So one member of that product is q, and you hold it here, right? That's q. If you differentiate q with respect to t, then you hold e to the t over rc. And if you differentiate e to the t over rc, you're going to have e to the t over rc times the derivative of t over rc with respect to t, which is 1 over rc. So the product is 1 over rc times q. So what you're looking at is the derivative of this with respect to t, and that is equal to e to the t over rc. Let me write this, let me make it look like c, over rc of v over r. Alright? So we have that. Then you integrate both sides. Now what you're doing here is finding the integral of a derivative. And you can consider the integral and the derivative as having cancel with each other. Oh, by the way, dt, I should have the dt. Don't forget to write the dt. It tells you that you're integrating with respect to t. Alright? Alright, so the integral and derivative, it's like they cancel out each other, leaving what you're differentiating or what you're integrating undisturbed. So what you have is 1 over rc times q is equal to, alright, this could be written as v over r because those are constant, integral of e to the t over rc dt. Alright? Now, when you integrate this, you're going to get v over r times e to the t over rc divided by, it's going to be divided by 1 over rc, right? Plus c, a constant c, or let's call it c1 in case we have to change it. Okay. We've run out of scrolling space, so let us draw a line and continue the work up here. Oh, I need to go to the left, alright, or to the right, I mean. Let's go up. Alright, so what do we have again? 1 over rc. This could be written as q over rc equals q over rc equal. So q over rc is equal to, let's scroll back down and see what it was equal to. V over r e to the t over rc. So we have v over r e to the t over rc. What else had happened down there? Divided by 1 over rc plus the constant. So it's divided by 1 over rc plus the constant of integration. Alright, good. Now, q divided by rc is equal to, this would be v divided by r, and then all of this multiplies this. Now, if you consider your fraction, this would be multiplied by rc over 1, and that times e to the t over rc plus constant of integration. Now q divided by rc is equal to, well, r would cancel, R. Alright? So what you have there is CV, C times V, multiplied by, that would be, where's the cursor? Hard to see the cursor. CV multiplied by e to the t over rc plus constant of integration 1. Alright? Now, let us multiply both sides by rc. Alright? So what we get is q is equal to rc squared v e to the t over rc plus rc times constant of integration 1, c1. Alright, now what we have there, right, is, so let me check back on something here. We had the integral of, okay, oh my, let's see, what were the constants again? E to the t over rc. So what we had here is q, and the other one, oh, I made a mistake here, you know. Looking back, oh boy, let me go back to this part, because the constants that we wanted, one of them is q, so it's q. The other one is e to the t over rc, right? E to the t over rc. How could I have done that? That was my mistake. Alright, so I'll have to just erase this part and then redo this part up here. Accidentally rewrote the e to the t over rc as something else. My. Alright, so before we go on, let's do a quick review and go back on track from that mistake. You have V, resistance, capacitance. Total voltage is the voltage drop across resistance plus the voltage drop across the capacitance, which is VR and VC. Alright? Now, Q equal to CV. That's the quantity of charge on the capacitor, is equal to the capacitance times the voltage. So the voltage of the capacitor, I could write this as C2, the voltage on the capacitor is equal to Q over C. We have that. And then the resistance now, the resistance voltage. Now, V is IR, right? Voltage up across the resistor is current time resistance. Now, at the same time, the current is the rate of change, or the rate at which charges are flowing into the capacitor as the charges are out of the capacitor as it discharges, right? So I is equal to dq by dt. So what we have is VR is equal to resistance times dq by dt. So we put them together, we divide by R, make it look like dy by dx plus py equal q, which you'll be familiar with. So divide by R, so we have dq by dt plus 1 over rc times q, right, divided by R is equal to v over R. Now the integrating factor is e to the integral of 1 over rc dt, which when you integrate 1 over rc with respect to t, you get t divided by rc. So you multiply both sides by the integrating factor, you get e to the t over rc times dq by dt plus e to the t over rc times 1 over rc times q plus, no, equals v over r times e to the t over rc. Now we use the product rule and see that this is the result of using the product rule to differentiate a product. What is that product? We found that it was q times e to the t over rc. Alright, so that now, it is the derivative with respect to t of this, and that's equal to e to the, let's put v over r first, v over r times e to the t over rc, and then we integrate both sides, integrate. So what we have then is q e to the t over rc, because we see the integral and derivative, like they cancel out each other, leaving the function undisturbed, alright, is equal to v over r dt. Don't forget the dt. Alright. E to the t over rc. This integral of e to the t over rc dt. Alright. So that's what we have. So what we have here then is q e to the t over rc is equal to v over r times, now we integrate this and we get e to the t over rc divided by 1 over rc. Alright, so that's what we have there. Now, instead of rewriting it, let's just copy. Alright, good. And we put the same thing up here and continue. Alright. Let's put it up top here. Alright, so we continue from there. So this is q e to the t over rc is equal to, well, this will be v over r times rc over 1 e to the t over rc. Oh, forgot to put the constant of integration. Right, after you integrate, you say plus c. Alright, call it c1 because we might have to change it. So what we have is plus c1. c1 is a constant of integration. Alright, so here we see that r will cancel r. So qe to the t over rc is equal to cv e to the t over rc plus c1. Okay, we want q, so let's divide by e to the t over rc. So q equals cv e to the t over rc divided by e to the t over rc plus c1 divided by e to the t over rc. Well, e to the t over rc cancel e to the t over rc here. So q is equal to cv plus, well, when you have c1 over e to a power, it's like c1 multiplied by e to the negative power. Remember your laws of indices. So it's c1 e to the negative t over rc. Alright? And here, so q is equal to, alright, now what we have our function here, alright? It's cv plus e, c plus a constant e to the negative t over RC. But suppose you consider that CV is really a constant. Well, the voltage is fluctuating, but you have a certain RMS voltage that is steady. Now, you can consider C1 a constant that's equal to CV. So, here, if you consider that to be CV, and you could consider it to be negative CV. I just want to fix it up, make it look a certain way. CV minus CV e to the negative t over RC. What you would get is that Q is equal to CV 1 minus e to the negative t over RC, right? You get something like that, right? But here we really had showed the equation involving quantity and the rate of charge. So Q is equal to CV plus a constant time e to the negative t over RC.